We present SAGA, a spectral adversarial attack on 3D meshes. This is a joint work with Itai Lang and Shai Avidan from Tel Aviv University. Suppose we have a mesh of a 3D shape as an input to an autoencoder. Normally, the input sphere mesh is encoded into a smaller Latin representation by the autoencoder and then reconstructed at the output. In our paper, we present the first geometric attack framework on 3D meshes. That is, we show that a small perturbation to the input mesh can fool the autoencoder to reconstruct a completely different geometric shape. Our adversarial sphere was reconstructed by the autoencoder as a cube. Triangular meshes are the primary representation of 3D shapes, with applications in many safety-critical realms. In the medical field, incorrect perception of the geometric subtleties of an organ can lead to life-threatening errors. In robotics and automotive, a precise understanding of the geometry of obstacles is essential to prevent accidents. Meshes are also used for facial modeling, where security is dependent on an accurate geometric perception of the mesh. Autoencoders are primarily used to reduce the dimensionality of meshes for storage and communication purposes. They are often utilized for segmentation, self-supervised learning, anomaly detection, and denoising tasks. In fact, autoencoders are the most prominent deep learning tool to process the geometry of meshes. Therefore, we believe it is crucial to expose their weaknesses and vulnerabilities. Our attack is formulated as an optimization problem with a source and target shape. We aim to find a smooth and indistinguishable perturbation of the source shape that will mislead the autoencoder to reconstruct the target shape. In order to create undetectable adversarial shapes with a natural appearance, we decompose the source mesh into its spectral eigenfunctions and perturb only a small subset of the lowest frequencies. The malicious mesh then passes through the autoencoder and we get a reconstructed output. While the weights of the autoencoder remain fixed, we use a loss function to optimize the spectral perturbation parameters. Our loss function reconciles two contradicting demands. On the one hand, we want to induce a small and unapparent change to the source shape. On the other hand, the adversarial shape must be sufficiently different from the source to effectively mislead the autoencoder and cause the target reconstruction. While SAGA is formulated in a white box framework, we show in our paper that it is also highly effective in a black box scenario against unseen autoencoders. We compare SAGA to another geometric adversarial attack against point clouds. In the top row, we see a mesh of a horse in the leftmost corner. In the rightmost corner, we see the target mesh of a leopard. The adversarial horse, besides the clean source, was formed by a geometric adversarial attack that was designed for point clouds. This attack, being adjusted to point clouds, causes distinctive distortions in the mesh surface by replacing the order of the vertices. On the contrary, SAGA applies low-frequency perturbations that preserve the underlying geometric surface. The bottom row shows the reconstructions of the shapes by the autoencoder. The clean source and target meshes were accurately reconstructed. SAGA's adversarial horse misleads the autoencoder to reconstruct the target shape of a leopard. The point cloud attack's reconstructed shape was also altered. However, it lacks the fine-grained details of the target mesh. Our attack stands in contrast to the semantic attacks in the literature. While a semantic attack aims to alter the prediction of a classifier to the target class label, we want to reconstruct the geometry of a target shape from the target class. In this experiment, we demonstrate that semantic attacks are not necessarily effective at the geometric level. In the top row, we see a clean source mesh of a cow in the leftmost corner. The adversarial cow beside it is an adversarial mesh that was created by a semantic attack and is capable of inducing misclassifications when applied to a classifier. The leftmost adversarial cow was formed by our geometric mesh attack. The bottom row shows the reconstructions of the shapes by the autoencoder. The clean mesh was accurately reconstructed. SAGA's adversarial shape successfully misleads the autoencoder to reconstruct the target shape of a hippo. The semantic adversarial shape is shown to be ineffective against the autoencoder, as the output geometry is similar to the reconstruction of the source cow. To summarize, we propose the first geometric adversarial attack on a mesh autoencoder. SAGA, our attack, presents stable reconstructions of target shapes using mild spectral perturbations of the source shapes. Our attack is effective in a white box and a black box framework. Our paper and code are publicly available.